Hello and welcome to the sixth week of getting started with competitive programming. So this week our focus is going to be on the shortest paths problem, which is both a very fundamental problem in graph algorithms as well as a really popular theme in contest programming. Typically, you're trying to figure out what's the fastest way of going from one vertex to another in a given graph. And in this module, which is broken up into 4 segments for your convenience, we are going to be leading up finally to this problem called sending email, and we're going to see Dijkstra's algorithm along the way. But before we get started, let me give you a high-level overview of the different scenarios that we will be addressing this week. So generally speaking, we will be working with graphs that are weighted and directed. To say that a graph is weighted in this context simply means that there is a weight function that maps every edge in the graph to some number. So actually your weights could be any collection of objects that you have the ability to add and compare. But specifically, we will typically be working with integers and sometimes rational weights. And to say that the graph is directed, we already know what this means from our discussions last week. But just to repeat, a graph is directed if we think of every edge as being oriented, or we think of the edges as being ordered pairs. So we distinguish for a pair of vertices x and y, we distinguish the pair xy from the pair yx. So that's going to be the setting that we are working in. Now we are going to start this off by looking at the special case when all the edge weights are 1. This is just another way of saying that you're working with an unweighted graph. Now in this situation, the nice thing is that the cost of a path is simply the number of edges on it. Notice that when you have weights, this need not be true, because depending on how the weights are, it could be that you have a path with a small number of edges that's super expensive, and you have paths with a large number of edges which are cheap, again, just because of the way the weights are. When all the weights are uniform, this is not something that you have to worry about. So the lengths of the paths are actually a true reflection of the cost of the path as well. Now this setting is simple enough that we have actually already seen an algorithm to resolve the problem in this case, and our first exercise will be essentially to recap breadth first search and consider how it helps us solve the shortest path problem in this special case. After this, we will allow for weights to enter the picture, and we'll see that BFS no longer quite works in its default form, and we'll have to explore a different way of approaching the problem. But we'll still restrict ourselves first to the setting when all edge weights are positive, because that's a little bit easier to think about compared to the more general case when we allow for negative edge weights. The thing about negative edge weights is that it can again mess up your intuition for what you expect to happen when you're dealing with shortest paths. So we are going to explore this distinction as we go along. So to begin with, we will not allow for negative edge weights, and then we'll allow for them. But when we do allow for them, again, we're going to do it in 2 phases. First, we will allow for the presence of negative edge weights, but we will disallow the presence of a negative weight cycle. Now, a negative weight cycle in a graph is simply a cycle which is such that if you were to go around the cycle and add up all the weights of the edges that you encounter, then the cumulative weight is going to be negative. Now, you'll have to take my word for this at the moment that this distinction is actually important. The presence of negative weight cycles can cause some substantial disruption in the notion of shortest paths. So we'll need to handle them carefully and separately. So in the setting when we also allow for negative cycles, we are going to see an approach that is different from the one that we take when we know or we assume that there are no such cycles. So this is going to be the essence of the 3 different approaches that we take to the shortest paths problem. First, we are going to see an approach when the graph is essentially unweighted, then we are going to look at an approach that works for positive edge weights, and we're going to modify that slightly to allow for negative arcs, but still we assume that there are no negative cycles. So I'm thinking of this as the second broad approach, and the third approach is going to be when we also allow for negative weight cycles, and we'll talk about that more when we get to it. Finally, we'll also deal with separately the problem of all pairs shortest paths. Now, it turns out that if you know how to do shortest paths, then you can more or less trivially also find shortest paths between all pairs by simply running this algorithm as a subroutine between all pairs. But it turns out that there's a slightly faster approach to this problem, which is very elegant, and we're going to explore that and implement it as well. So as is usually the case, we are going to describe these algorithms and describe their implementations, but we will not really have the time to get into proofs of correctness, which are also important to just have a feel for and to appreciate and understand. So if you're curious about which algorithms we are going to be learning so that you can go look them up in more detail after we are done, then I'm just going to throw in the names here. So first, the case of unweighted graphs, as I mentioned, is really the breadth first search traversal that we discussed last time. And the case when all edge weights are positive can be handled by Dijkstra's algorithm, and a slight modification to Dijkstra's algorithm makes it work even when we have negative edge weights, but we don't have negative weight cycles. Once we do allow for the possibility of negative cycles, there's the Bellman-Ford algorithm, which allows us to either determine the shortest paths correctly or detect the presence of such a cycle. And once again, when we get to this discussion in more detail, you will see why this sort of output actually makes sense. And for all pair shortest path, the improvement that we are going to look at typically goes by Floyd-Warshall. Now, I should mention that shortest paths being a really fundamental graph algorithms problem has been extensively studied, and some of these algorithms were proposed by several other researchers who are not mentioned on this slide. So if you're interested in the rich history of shortest path algorithms and how some of these really popular ones came about, I would highly recommend the chapter on shortest paths in the algorithms text by Jeff Erickson. This book is conveniently available from the textbook's website, and I'm going to add a link that you can follow in the description of this video. So please do check it out. It has many more details about how these algorithms came about, and there's a nice historical perspective that you will gain if you were to go through this. In the meantime, let's now get started with the special case when all edge weights are 1. That'll be the focus of this segment, and in the next 2 segments we will consider Dijkstra and modified Dijkstra's approaches, and we will round this off by looking at an implementation in the context of the sending email problem. So that's going to be the plan for this module. In the next module we will look at Bellman-Ford. Again, we will split it into 2 segments. In the first, we will study the algorithm itself, and in the second, we will implement it in the context of a problem. And then in the third and the final module, we are going to do the same for all pairs shortest paths as well. Okay, so that's the outline. Now let's get started with the first case, and let me just begin by recapping the definitions for you here. So as we said, we will be working with weighted directed graphs. Typically, you might imagine that you've been given 2 vertices, which we will usually refer to as the source and the target, and you're trying to figure out what is the path that connects the source to the target that has the cheapest cost. The cost of a path is simply the sum of all the weights of the edges that participate in the path. So this quantity that we have just described here is often referred to as the distance. So we will talk about the distance of the vertex T from the source S as being the length of the shortest path that connects S to T. Now, this problem that we have just described is often just called the shortest path problem. So you're given two vertices S and T, and you want to find the length of the shortest path from S to T. A very popular variant is the single source shortest path problem, SSSP, where you're given a source vertex and you want to know the distance of every other vertex from this source. And this is something that you can of course solve by just solving shortest path individually on every vertex. That's a valid algorithm, but sometimes it's just useful to think of this more holistically, and you could come up with better ideas which solve SSSP in one shot, so to speak. And the SSSP problem will pretty much be our focus for all of this module and even the next one. But after that, we will turn our attention to this all pair shortest path problem, which is again a very popular variant. So here we want to know the distances between every pair of vertices in the graph. And once again, of course, if you know how to do SSSP, you can do APSP by simply running SSSP as a subroutine, right? So you run an outer loop which runs through every vertex, and for every vertex you just run your SSSP algorithm, and you will then end up having discovered the distances between every pair of vertices. Now that is going to have a certain complexity, which is basically the complexity of the SSSP algorithm with a multiplicative overhead of n being the number of vertices. And an interesting question is, can you do better? Can you somehow solve APSP directly? And it turns out that we will have some ideas to address that question as well. So these are the three problems that we will be considering. And before we actually get to trying to understand what happens when all edge weights are 1, let me also get a little more terminology out of the way. So you might remember from the previous week that we defined a path as a sequence of vertices where every consecutive pair is connected by an edge. And in the context of directed graphs, you want the edge to be from, say, ui to ui plus 1 if you're looking at the ith and the I plus 1th vertices in the sequence. So they have to be oriented exactly in the way that you expect them to be. So that is a path. And notice that when we define a path, we don't really have any constraints on whether vertices can repeat or not. So by default in a path, you could have a repeating vertex. And if you insist that you don't want vertices to repeat, you want all the vertices on the path to be distinct, then you emphasize that by calling it a simple path. So whenever we refer to paths, we will generally speaking allow for repetition of vertices. If we want to emphasize that vertices are not being repeated, then we will use the phrase simple path instead. Now, as long as you're working with non-negative edge weights and you want to observe shortest paths, this distinction is not very important because all of your shortest paths will automatically be simple paths only. To see this, let's look at an example of a path which is not a simple path. So here, for instance, starting from S, suppose we go to T in this way. So notice that the vertex X is getting repeated and then we finally land up at T. And imagine that all the edge weights are 1 here. It should be reasonably obvious that this is not an optimal path from S to T, because this whole detour that we did on the cycle XRQP could have simply been avoided. So whenever you have a path with these repeated vertices, if you just eliminate the detours, then you will see that you always end up with a path that is better than the one that you started off with. So as long as your edge weights are non-negative, your shortest paths will automatically turn out to be simple paths. From this example, you can probably already start getting some sense of why negative cycles can be problematic for the definition of shortest paths. This is something that we will explore more fully later, but I just wanted to drop a hint in case you were curious about that. But just going back to our definition here, this is just a reminder that whenever we talk about paths, in general, we will allow for repeating vertices. And whenever you're working with non-negative edge weights, your shortest paths will automatically turn out to be simple paths anyways. Now, in terms of terminology, I should also point out that in some references, in some textbooks, especially graph theory textbooks, what we are calling a path is usually called a walk or a trail. Okay, and what we are calling a simple path is actually just called a path. So this can sometimes be confusing depending on where you're reading from. So it's just useful, I think, to fix one terminology and stick to it in a particular discussion. And since this is the tradition in most algorithms books that you will read, I will just stick to this terminology, where a path is a sequence of vertices where the consecutive vertices have an edge between them and the vertices need not be distinct. And if I want to emphasize that the vertices are distinct, I will refer to it as a simple path. So with that out of the way, let's finally talk about what can we do when all the edge weights are 1. So for this special situation, as we have hinted to earlier, we already know an algorithm that determines the distances from any source vertex for us, and this is in fact the breadth first search, or the BFS traversal, that we have seen in the previous week. So in fact, let's pull up the implementation to remind ourselves of what we were doing. So we had this distance array, which was initialized so that every vertex was initially at a distance of infinity from the source, meaning that these were all unexplored vertices and we don't know anything about how close or how far away they are from the source in the beginning. And the only thing that we know is that the source is immediately reachable from itself. So the distance from the source to itself is initialized to 0. And after this, we had an implementation where we essentially explored all the neighbors of the source first, and then the neighbors of the neighbors, and so on and so forth. At every stage, we were careful to not revisit an already visited vertex. And if you draw out a typical BFS traversal, you'll see that there's a natural layer-like progression. The BFS tree can be organized fairly naturally into layers, and it turns out that all the vertices that are in the kth layer are in fact at distance k from the source, and this is something that you can prove. Now, although we won't be doing a formal proof of why BFS works as claimed, I would like to go through an example just to build some intuition for why you might expect to believe that this works out the way that it does. For this, it's crucial to understand how vertices enter the kth layer in the BFS traversal. Now, our code here already has a trigger which helps you understand when a new layer has started. This is the first time that the distance of the vertex that you're currently exploring mismatches with the layer number that you're currently storing. So when that happens, you can print a statement saying that a new layer has just begun, and of course after that you update the layer variable and so on. But to help our visualization along, I'm just going to introduce a conceptual intervention here, which is the idea of using a token to keep track of what is going on with the layers. So this token is a completely artificial concept. It's just in our imagination. You don't have to change or update your code or anything like this. Just follow along with the example that I'm going to show you. So the way the tokens are going to work is that to begin with, we are going to enqueue the source and a token right behind it. And in general, at any step, if we pull a token from the head of the queue, then we'll just take the token and push it back to the end. Now, the idea is that whatever vertices are sandwiched between these two token operations, so to speak, are the vertices that get into a common layer of the BFS traversal. I think this will become clearer as we go through an example, so let's do that. So here is a graph with a source vertex that's been highlighted. So to begin with, as we said, we have on the queue the source vertex followed by a token. Now, when we are currently processing the vertex at the head of the queue, what does BFS do? It's going to figure out what are all the neighbors of this vertex that's currently in the limelight, what are all of its neighbors that have not been visited yet, and we are going to collect all of those vertices and push them to the back of the queue. Now, since this is the very beginning, no vertex has been visited so far, so we will just pick up all of the neighbors of S. In this case, there are 3 neighbors, X, Y, and Z, and we are going to push all of these to the back of the queue, and we are going to mark them as visited. Now, As you can see, S left the queue and we pushed the token to the back because the token was the next thing on the queue. And now the next vertex to get processed, the vertex in the head of the queue, is the vertex X, and X has 2 unvisited neighbors. I mean, it has altogether 4 neighbors, but only 2 of those are unvisited so far. So we are going to queue these up, R and P, at the end of the queue, and we're going to mark them as visited. Let's bring the queue a little bit into the left so we have a little more space. And at this point, we have finished processing the vertex X, so we will let X exit the queue. And now I'm going to color code X with a different color because this is, notice, a shift in the layer number. So we have the first layer is by default just the source vertex, and now until the next time that we see a token, all the other vertices are going to be on the first layer. So I'm going to mark all of these vertices yellow just to remember that these have been processed and they were members of the first layer. So the second vertex in the first layer is the vertex Y. So this is our current active vertex. It has only 1 unvisited neighbor. So we are going to identify this neighbor T and push it to the back of the queue. Now we'll let go of Y. And again, mark it as a vertex that was processed as a part of the first layer. Now the last vertex in the first layer is the vertex Z, and Z has 2 unvisited neighbors. So let's identify U and V. So we go ahead and add U and V to the back of the queue. At this point, we are ready to let go of Z, and we also remember to mark Z as the last vertex to be processed in the first layer. Now we see the token, which is a signal that we have finished processing all the vertices in the first layer. So we push the token to the back, and we are now mindful of the fact that we have started off a new layer, which in this case is going to be the second layer. So let's see what happens in the second layer. The first vertex at the head of the queue is the vertex R, and R only has 1 unvisited neighbor, which is Q. So we identify Q and add it to the back of the queue, and then we let go of R. When we look at P and T, which are the next vertices in the queue, they have no unvisited neighbors, so we simply mark them as being processed. And notice that now the color coding has changed to denote the fact that we are processing vertices in now the second layer. So the next vertex is U, and U does have an unvisited neighbor, which is W. So we add W to the back of the queue, let go of the vertex U, mark it as processed, and finally we see V, which has no unvisited neighbors, so we simply let it go and again mark it as being processed. And the next thing on the queue is the token, which tells us that we have finished processing all the vertices on the second layer, and this marks the start of a new layer, which in our case is going to be the third layer. So as before, we push the token to the back and we process the 2 vertices that we have on the third layer. None of these vertices have any unvisited neighbors, so we are simply going to run through them and let them go and just mark them as being vertices in the third and in our case also the last layer, because now the only thing left in the queue is the token, which is a sign that BFS has run its course and the algorithm is now complete. So if you were to look at the sequence in which the vertices got processed organized by layer, you'll see that this is how everything panned out. So we started with the source, which was on layer 0, and then in the first layer we saw its immediate neighbors X, Y, and Z, and X, Y, and Z were responsible for pulling in collectively the vertices R, P, T, U, V on the queue. That constituted the second layer, and these guys brought in Q and W. Hopefully it's intuitive that when you are on layer number K, you are at a distance of K from the source. It's clear that you're definitely reachable within K steps. That's for sure, because you can just follow your parent pointers and trace your way back to the source. The only question and the thing that actually requires a proof is to say that you cannot do it any faster. You cannot do it with fewer steps. And the intuition for that is that if you could do it with fewer steps, then you would have been recognized and you would have been pulled in earlier in a previous layer. This is something that you can formalize using induction. And here are a couple of statements that you may want to think about proving. If you haven't seen a formal proof of this in a previous class, it's worth sitting down and trying to work through this. So essentially we're saying that when you are at the end of the kth phase, when you look at a vertex, its distance is either infinity. So this is distance as recorded in the distance array. So either it's so far an unseen vertex, or if it's a seen vertex, then the value that is recorded in the distance array is going to be at most k, and it's exactly k if and only if you are in the queue at the kth phase. Also, the correctness of BFS in the context of capturing distances is given by this claim here, which says that once BFS is done, the values in the distance array are a true reflection of the actual distances in the graph. This is something that you can prove using induction. As usual, I'll not be going into a proof here, but if you're interested, you could either try figuring this out on your own, or you can look up the pointers in the description of this video where you can read up on a proof of this fact. So the main takeaway from our discussion so far is that if you have an unweighted graph, then BFS is your best choice in terms of computing distances between vertices. However, once edge weights come into play, then BFS might not work out. So in particular, you could try to pause the video here and come up with an example of a graph where BFS does not do the right thing in terms of capturing distances when edges have weights on them. So feel free to pause the video here and come back once you've had a chance to think about this. All right, so here is an example. It's a graph with just 3 vertices, and the edge weights are as shown. And you can see that if you're trying to figure out the distances from the source to all the remaining vertices, then the best way to get from S to B is not via the direct edge, but to actually take a detour and go via A, because that's how the edge weights have been set up. On the other hand, because the way BFS works, the algorithm is not really trained anywhere to account for the weights at all. It's just going to blindly pick up both the neighbors of S in the first layer of the exploration. So both A and B will have the same status as vertices on the first layer, and if you were to do backtracking to find the shortest path, then BFS would tell you that the best way to reach B is via the direct edge from S, which in this case is not quite right. And it's not surprising, once again, because BFS is really not trained to look at weights at all. So you could try to fix this in some sense by making BFS see the weights by potentially messing around with the graph a little bit. So one thing that you could do, which is actually a pretty common trick, is to puncture the edges that have weights on them as many times as the weight, roughly. So actually weight minus 1 many times, so that the edge, which previously was just a direct edge, is now automatically elongated to reflect the actual weight of the edge. Now, of course, this will work as long as your weights are positive integer weights, so that you can do this puncturing an appropriate number of times, and you can convince yourself that if you run BFS on this modified graph, things will actually work out and you will get the correct distance values. So this feels like a tempting way to prolong the usefulness of BFS. So at least when you have positive integer weights, maybe you can actually do this. Would I recommend it? Well, unfortunately, no, not really. The reason for that is that this operation of subdividing the edges and inserting these artificial dummy vertices can be extremely expensive. And in particular, the graph that you generate by doing this trick the number of vertices in this graph, as you can imagine, is going to be proportional to the weights of the vertices. So if you have the weights of the edges, so if you have edges whose weights are rather large, you are going to be creating a humongous graph that you don't really want to deal with. Instead, what you might want to think about is come up with a way to predict the behavior of BFS. Really, the key thing that you want to think about is what is the next real vertex, not the dummy vertices, but what's the next real vertex that BFS is going to add to the queue in this modified graph. And if you can distill the essence of BFS's behavior on this graph, if you can predict properly which is the next vertex that gets added to the queue, then hopefully you can bypass the creation of this intermediate graph and you can directly write an algorithm that will do the right thing for graphs that have non-negative edge weights. So that's more or less what we are going to do, and that's going to lead us to a discussion of Dijkstra's algorithm, which is what is coming up in the next segment of this video. So before you watch that, maybe just think about what would be your strategy to deal with edge weights, especially when you don't have to worry about negative edge weights. I'll see you back in the next segment.